In this video I'm going to do some simple analyses of a Chip-Seq dataset. The dataset in question is a histone modification dataset taken from the ENCODE project. I'm going to start off by importing the data. So if I go to File, Import Data, the data is available in a BAM file that I've previously mapped, and I'm going to import just one file. In the BAM file options, this is a single end chip dataset, so I'm going to extend all of the reads by 200 bases. The reason I'm extending the data is because what we're interested in a chip dataset is the position of each enriched fragment, but we don't sequence the whole fragment, we simply sequence a short tag from the end of the fragment. If you do paired end data, then you can infer the position of the full fragment by looking at the two ends, but in single end data you can simply extend the read that you have to infer roughly where the whole fragment sits by knowing what the insert size of your library is. Because I've extended my data rather, I've got some warnings that have come from the import. The warnings tell me that a few of my reads stepped over the end of my chromosomes, but because they stepped over by less than the distance that I extended the reads, I can ignore these. I can quickly see from my data that I have obviously enriched regions, and the first thing I'm going to do is to run a peak caller to try and identify where all of these regions are. The peak caller can be found under the Data Define Probes menu, and under there we have a re-implementation of the max peak caller. We need to tell it which datasets we want to call, and in this case I only have one. If we have an input sample, then we can use that as a control, but in this case I don't have, so I'm going to leave that unchecked. I'm going to start the caller running. What the caller does is initially do a pass through the data, finding what it terms high confidence peaks. These are very enriched regions, and it uses these to determine if there is a generic offset between the forward and reverse strand reads in our data so that it can correct for this. Because we've extended our reads, we wouldn't expect there would be much of an offset, but the algorithm will still check this. Once it's gone through and found its initial set of peaks, it will then do a full pass through the data, looking for levels of enrichment which are significant above the threshold that you specify when you first run the algorithm. This initial set of candidate peaks will then be validated in a second pass, where the level of significance will be assessed not against the global level of coverage of your genome, but using local levels of coverage in either your input sample, if you have this, or in the actual sample itself at wider windows around each of the candidate peaks, if that's all that you have available. So that's what it's going to do here. The initial peak detection takes a little bit of time because it does a sliding window analysis over the whole genome, but the validation of the candidate peaks should be fairly quick. Once we have the set of peaks, I'm going to quantitate those and then show you how to create a report if you want to look at those, and also how you can prepare a figure for publication if you want to show an example peak. Right, once we've got the peaks in, I'm just going to do a read count over the positions that have been identified so that you can see where they are. So here we can see that all of the regions of enrichment have been identified, and we can quantitate these. We can do something simple like having a look at the range of values that we get for this, and we can see that we have a distribution of levels of enrichment even within our sample. If we wanted to make a list of all of the peaks that we've got here, we can create an annotated probe report from them. I'll annotate each of these with the closest gene, and that would then produce a list of all of the peaks that we found, and with their relative strengths in this last column here. So if I wanted to find the strongest peak, it would be here, down to the weakest peak that was found, which will be down here. If I wanted to prepare a figure for publication to illustrate some of these peaks, one useful thing to be able to do is to turn the list of peaks into an annotation track. I can do this by going to File, Import Annotation from the active probe list, where the active probe list is the result of the peak caller. I'll name this annotation track peaks, and you can see now that I have an annotation track going over the peaks. If I wanted to illustrate a couple of example peaks, I can do this by reconstructing probes that are tiled over this region and quantitating them so I can get an enrichment view. So to do this I can use a quantitation pipeline where I construct what's termed a wiggle plot over the currently visible region. The scaling will be a bit off from this, but if I zoom out I can see the region better, and by putting it in a single colour it might look a little clearer. I can see that if I go into one of these peaks that there's some bumpiness inside the peaks and it might benefit from a little bit of smoothing. So if I want to smooth this off a bit, again I can go into my quantitation options and smooth it over a number of adjacent probes. And if I just want to see the quantitation, then I can show my smoothed peak, and that would be something that might be suitable for going in a publication to illustrate a typical peak that was found. Going back to where my original peaks were detected, I can see that the majority of these sit at the start of transcripts. So another way of looking at this kind of data is, instead of doing a peak detection, to systematically look at all transcription start sites in the genome. I can put probes over all of my transcription start sites by defining probes using the feature probe generator. In this case I'm going to use the mRNA feature track, and I'm going to put an upstream probe so that it centers around the transcription start site, and put a probe that spans 2 kilobases either side of this, and then just do a read count over that. So having covered every transcription start site, I can now go back and look at my probe value distribution, and I can see a fairly clear bimodal distribution where the suspicion is that I have a set of transcription start sites which are enriched for this histone modification and a set which aren't. I can also look at these regions in another way. Rather than just counting how many probes are in each how many reads are in each probe, I can look at the distribution of the reads across each probe by constructing a probe trend plot. If I do this, I can see if there is a pattern to the enrichment within the sets of probes that I've constructed, so whether there is a positional bias around the transcription start site. And in this case, remember, I constructed the probes to be 2 kilobases either side of the transcription start site, so that would place the transcription start site about here. And I can see very clearly that there is an obvious enrichment which centers just after the transcription start site, about 150 bases after it. So I could, if I wanted to, quantitate more thoroughly by selecting a region maybe 500 bases before the transcription start site up to 750 bases after, and that would give me a more accurate quantitation genome-wide without having to do any kind of peak detection. In addition to the probe trend plot, which just simply gives me an average trend across all transcription start sites, I can also look to see if there might be multiple different patterns of enrichment around the transcription start site by doing something called an aligned probes plot. So if I do that, the aligned probes plot puts a line into the plot for every transcription start site, and the depth of colour along that line illustrates the depth of read coverage. So if I adjust the contrast a bit using the slider on the right, I can see that again, for about half of the transcription start sites, I see enrichment around the centre of my probes. For the other half, it really doesn't happen. If I look down here, there's no real pattern to where the remaining reads go, which fits with what we saw from the bimodal distribution. And again, you can see that there's a clear pattern of enrichment towards the centre with a little bit of a dip before, which is exactly what we saw. So in these two simple ways of looking at Chip-Seq data, we can either get a global view of the enriched regions using a statistical analysis, or we can look thoroughly at every single transcription start site, looking at the bias of positions around it and quantitating over those regions.